Okay, guys, the time has come. Probably you're not aware about this, but we should start. Okay, first of all, I want to recall what we did the last time. It's like, you know, I know what you did the last summer. This is the same thing. We discussed polynomials in several variables. F is a field. x1, xn are the variables. This is the ring of all polynomials in variables x1, xn with coefficients in F. Then we defined a lexicographical ordering on monomials, or monomials are just the products of variables. So first of all, we need to fix the ordering of the variables, and then we can define the lexicographical ordering on the monomials. Then, when we know how to compare the monomials, we know what is a reduction. So we define a process of a reduction. First of all, we know the notion of an elementary reduction. And then if you make several steps, this is what is called a reduction, and it's denoted by a set. And R is a result of the reduction. And if you cannot reduce R any further, then R is called a remainder. So if the reduction is not possible, so if you cannot reduce, then this thing is called a remainder. Well, with respect to the set of reducers here. Okay, so this is what we discussed the last time. So this procedure is very similar to the procedure of Euclidean division in case of one variable. Now, the last time we discussed two facts. The fact number one is whether the process stops or not. Well, actually, we proved that the process of reduction always terminates, and after finitely many steps, you will get a remainder. But there was a problem. If you're given an arbitrary set here, it may happen that for some polynomial, one chain of reductions leads to a remainder R1, and another chain of reductions leads to a remainder R2, and these two remainders are not the same. So this is the kind of issue we don't want to have. So today I want to discuss this issue. And actually, we define the notion of a Gröbner basis. Let me recall a definition that a subset G from the set of polynomials, let's say non-zero polynomials, I don't want to have a zero polynomial inside of G, is called a Gröbner basis if for every polynomial and every chain of reductions with respect to G to R1, where R1 is a remainder, and every chain of reduction to R2, these two remainders are always the same, which means that every chain of reductions to a remainder leads to exactly the same remainder, which means that if you have a Gröbner basis and you want to reduce something by this Gröbner basis, you will always get exactly the same remainder, and there is no issue like that. So this is a very good notion because, well, you will be able to solve effectively different problems using Gröbner basis. I will discuss these problems at the end of this lecture, but before doing that, I want to discuss how to check if something is a Gröbner basis. So how to determine that we're given a Gröbner basis. So before doing that, I want to define some auxiliary notion, a definition. Well, suppose we have two polynomials, f and g, here. Now, as usual, we can represent the polynomial f as the leading coefficient, C1, the leading monomial m1 plus the tail of the polynomial f. Well, if we are given a lexicographical ordering, because if we don't have an ordering, we cannot order the monomials, and it's impossible to tell which one is the largest one. But if we have an ordering, then we can fix the largest one here. The same thing happens in case of G, so this will be C2, M2 plus G0. So these are the highest monomials of the corresponding polynomials. Now, I want to define the notion of an S polynomial of f and g. This S polynomial is required to formulate a criterion for being a Gröbner basis. So S polynomial is, well, it's a polynomial which can be produced using f and g. So what will we do? So first of all, let's take the monomials m1 and m2, and I want to compute the least common multiple of m1 and m2. Okay? So let's say this is m, the least common multiple. So for each variable, we just take the highest power between powers in these two monomials. Now, after that, since this is the least common multiple, we can represent it as the product of T1 and M1 and as the product of T2 and M2. So basically, T1 is M over M1 and T2 is M over M2. Now, what I want to do, I want to multiply F by T1 and G by T2 such that the leading monomials of F and G became M. And then I want to subtract one from another one with sufficient coefficient such that the leading terms are cancelled. So this is what I want to do. So what I'm doing, so I take F and G. I multiply F by T1 and G by T2. Then the leading monomial here is M, and the leading monomial here is also M. But the leading coefficient here is C1, and the leading coefficient here is C2. So I multiply this by C2, this one by C1. So now the leading monomial and the leading coefficient here and here are the same, so I can subtract one from another one. And the result is called the S polynomial of F and G. So what basically happens here, if I rewrite these explicitly, so as you can see, the product of these and these two guys will give you M, and the product of these two guys is exactly the same. So after opening the parentheses, this thing and this thing, they cancel each other, and the result will be C2 T1 F0 plus, minus C1 T2 G0. So this is another expression for the S polynomial when you use the tails and the corresponding monomials. So this is by definition S polynomial of two polynomials. Okay, just in case for those who just came, here I just recalled what we did the last time and the definition of a Gröbner basis, and here was the definition of an S polynomial. So let me go through the definition again. When you have two polynomials and a lexicographical ordering, you can represent each polynomial as the leading term plus the tail. Now what you do, you take the two monomials, you find the least common multiple of these two monomials, and you find the corresponding factor in order to multiply it and get the least common multiple, okay? Then you multiply F by the corresponding common multiple to get this monomial as the leading one. You multiply G by the corresponding factor to get this monomial to become the least common multiple. Then you multiply them by the leading coefficients C2 and C1. And then when you subtract this guy from this one, the leading terms of these two polynomials, they cancel each other. So as written here, so you will get some polynomial, and by definition, this polynomial is called as polynomial of f and g. Okay? So, because we will need this notion, because this notion will be used to formulate a criterion for a set to be a Gröbner basis. Okay, so yeah, so let me give you an example. So an example, let's take the ring of polynomials with rational coefficients with variables x, y, z, and we take the lexicographical ordering where x is higher than y and higher than z. And the polynomial f will be xy minus 1, and the polynomial g will be yz minus 1. Okay, there is no leading coefficient here. Okay, let's take 2 to be the leading coefficient here in front of g. I think it will be more interesting. Now, what is the leading monomial of f? The leading monomial of f is xy. The leading monomial of g is yz. So the least common multiple will be xyz. Now, what should we do by definition? We take f, which is xy minus 1. We take g, which is 2yz minus 1. Now, we multiply this polynomial by a monomial to get the least common multiple. Here we should multiply it by z. And here, in order to get the least common multiple, we should multiply by x. Now the leading monomials of these two polynomials are the same. Now we need to make the leading coefficients to be the same. Here the leading coefficient is 2, here the leading coefficient is 1. So we multiply this by 1 and this one by 2. And now we subtract one from another one. So these two parts, they cancel each other. And the result will be x minus 2z. So by definition, this is the S polynomial of f and g. So this is how to compute the S polynomial of two polynomials. So it's well defined, it's uniquely defined. I mean, for a pair of polynomials f and g, there is only one S polynomial. Okay, are there any questions regarding the definition, just in case? Okay, now let me formulate the Buchberger criterion for a set to be a Gröbner basis. So the claim. The Buchberger criterion. So what do we have? We have a set G of non-zero polynomials. The reason why I have this assumption that all the polynomials are non-zero because I want to find a leading monomial of every polynomial in G. If a polynomial is 0, there is no leading monomial, so it doesn't make sense. Okay, now we have a lexicographical ordering fixed. So at least one of them should be used here. Now, when we have a set of polynomials and a lexicographical ordering, then the notion of a Gröbner basis is well defined. Because for being a Gröbner basis, we have to have a reduction process, but in order to have a reduction process, we have to fix a monomial ordering. Now, this set, the following are equivalent. The condition number 1, G is a Gröbner basis. The condition number 2, for every pair of polynomials from G capital, f and G small, there is a reduction of the corresponding S polynomial to 0 with respect G. So if you take every pair of polynomials from G, you produce the corresponding S polynomial, you can find at least one way to reduce it to 0. Now, a condition number 3, for every polynomials f and g from G capital, every reduction leads to 0. So So roughly speaking, the set of polynomials G is a Gröbner basis if and only if every S polynomial for polynomials in G reduces to 0 with respect to G. And reduces to 0 can be formulated in two ways. The first way is to say that there is at least one reduction that leads to 0. And the second option is to say that every reduction leads to 0. And these two are equivalent. So if every S polynomial has at least one way to be reduced to 0, then actually every way gives you a 0 remainder. So the condition number 2 is the condition that is easy to check. Because let's say you want to check if something is a Gröbner basis. Well, it's enough to show that each S polynomial has at least one way to be reduced to 0. And if you want to prove that something is not a Gröbner basis, you should show that for at least one pair of polynomials, you can find at least one way to reduce the S polynomial to a non-zero remainder. Then it's not a Gröbner basis. So let me demonstrate the criterion in this particular case. Let's say we want to consider the set G consisting of F and G small. Okay? Now, we already know that the S polynomial is this guy. Now, let's see. Is it possible to reduce the S polynomial to 0? With respect to this set. Let me. Why? The answer, I like the answer, but now I need the reason. Okay, first of all, how do we do a reduction? In order to make at least one step of a reduction, we need to find a monomial here divisible by the leading term of at least of one of these two polynomials. But as you can see, neither of them is divisible by the leading term of these two polynomials because these two monomials are of degree 1 and these two guys are of degree 2. So these and these, they do not divide the monomials here. So this is a remainder already. So it's not possible to proceed with the reduction process. So that's why, well, since this is a remainder, so the empty reduction process where you did 0 steps leads to a non-zero result, to a non-zero remainder. So that's why, by this criteria, by the third part, so there exists a pair and there exists a reduction leading to a non-zero result. This is not a Gröbner basis. Okay? Who was able to follow, just in case? Good. Okay. Now, sometimes it happens that, well, you can predict that the S polynomial can be automatically reduced to 0. So you can skip this verification process because technically the hardest part of this criterion is the reduction process because, well, it's tedious. You have to apply a lot of steps, and if you have a very big set and very complicated S polynomial, so it may take a long time. But sometimes you can predict that the S polynomial can be reduced to 0 automatically. Let me discuss this special case. The claim. So suppose we have two polynomials, f and g. I'm sorry. Lexicographical ordering is fixed. Now, suppose that the leading monomial of f and the leading monomial of g, they are coprime. Okay? Then the S polynomial of f and g can be reduced to 0 with respect to f and g. Yeah, by the way, I want to skip the proof of this criterion, and I will prove the criterion during the following lecture. But today, I just want to discuss the criterion and its corollaries. So the proof will be during the next lecture, and we will use the whole lecture to prove the criterion. OK, but now this is a different kind of statement. This statement says that if we have two polynomials with coprime leading monomials, then their S polynomial will be reduced to 0 automatically. OK, and actually, we will see that actually every reduction will lead to 0. Like, it doesn't matter which reduction you choose, you will always get a 0. Just in case, are there any questions regarding the claim itself? Should I clarify the statement or? OK. Should I provide an example before we prove the claim? OK. Let me give you an example. So let's say in the same ring of polynomials, x, y, z, if we take xy square minus z and z square plus 1, this is f, this is g, and let's say the lexicographical ordering is fixed like this, then the leading monomial here is xy square. The leading monomial here is z square. So they are coprime. They do not have a common factor. The set of variables is completely different. So that's why if you produce the S polynomial of these two guys by this claim, it will be reduced to 0 automatically. You don't have to do this. Like, you just know this by the claim. So this is how it works. By the way, if you choose a different lexicographical ordering here, if you say the z is the highest, then the leading term here becomes z, and the leading monomials are no longer coprime. So this property depends on the choice of the ordering. Like, I mean, if this can be true for one lexicographical ordering, but it may not be true for another lexicographical ordering. So if you don't care about the ordering, you may try to find a lexicographical ordering where this has happened for the majority of the pairs of the polynomials you are given. Now, let me prove this. First of all, let's represent the polynomial f as here and the polynomial g in the same way. Now, we know that these two monomials are coprime. So the least common multiple of m1 and m2 is just the product m1 times m2. So by the definition, the S polynomial will be computed as follows. F and g here. So we should multiply these by m2 and this one by m1. Multiply this by c2 and by c1 and subtract one from another one. So this is by definition the S polynomial. Now, if we substitute these two expressions here, well, and we just repeat this computation, so the leading monomials will be canceled, and we will get the tails here. So what we will get here will be c2 m2 f0 minus c1 m1 g0. So if you just substitute these two polynomials here, this is the result you will get. Now, before proving that you can reduce this polynomial to 0, I want to rewrite this expression in a different form. And the reason why I can do this, you see, because these two monomials were coprime, the least common multiple is the product of these two monomials. And we multiplied f by the leading monomial of g and g by the leading monomial of f. So I want to express m2 in terms of g and M1 in terms of F. So I want to substitute here what? F minus F0 over C1. F minus F0 over C1. And I want to substitute here G minus G0 over C2. G minus G0 over C2. OK? Now, what will we get? The S polynomial of F and G can be expressed as what? C2, then, I'm sorry, that was incorrect. Here is G, here must be G, and here must be F, because M2 corresponds to G and M1 corresponds to F. That was a mistake. So let me rewrite it here. So M2 must be written as G minus G0 over C2, F0 minus C1, and here F1 minus F0 over C1, G0. So if we rewrite it here, am I doing something wrong? No, that's okay. That's okay. That's actually okay. So now, so we cancel these two things, and in the result we will get F0G plus minus G0F. Okay, so this is how you can rewrite the expression. So the S polynomial can be presented as this sum, where G and F are the initial polynomials. And what can we say about these guys? Well, what is important, every monomial here is strictly smaller than the leading monomial of F. And every monomial here is strictly smaller than the leading monomial of G. So every monomial here is strictly smaller than the leading monomial of F. And every monomial here is strictly smaller than the leading monomial of G. So now I want to prove a more general statement. Suppose we have a polynomial of the form A times G plus B times F, where every monomial of A, well, A and B are polynomials, also here, and every monomial of A is strictly smaller than the leading monomial of F, and every monomial of B is strictly smaller of the leading monomial of G. And now I want to show that no matter which A and B with these properties we chose, this thing can be reduced at least once, either by G or by F. So you can always reduce this expression. Now, okay, again. So what I want to show you that in this situation, if it's it's always possible to reduce this expression at least once. But now, let me explain why this proves the claim. And then I will explain why it's possible always to reduce this expression. Now, how to derive the claim from this fact? Well, you see, let's start the reduction process using F and G. We know that this process will terminate. But if we apply the reduction process here, okay, so I have to show one additional step. So let's show the following. So if we have a polynomial like that, and we reduce it, let's say, by G, then the result will be a polynomial, will be an expression with the same property. So it will be of the same form, and the monomials here and here will be, the monomials here and here will satisfy the same properties. So if we show this, then we can show that the reduction process will always be 0. Why? Because, well, let's start the reduction process. If we know that after each reduction, the expression of this form becomes an expression of this form, so the remainder must also be an expression of this form. So if the remainder is not 0, so then you can proceed with the reduction process. So this is a contradiction. So in order to prove what we want, we need to show that, first of all, if this polynomial is not 0, we can always make at least one step of reduction. And the second step part, we should show that the result of the reduction will be an expression of exactly the same form. So this will allow us to show that the remainder is always 0. Just in case, who was able to follow the explanation in general? Who thinks that it was vague and it requires an explanation? OK, just in case, let me prove these two auxiliary statements, and then I will repeat the whole process again, just in case if it wasn't unclear. So the statement number 1, I want to show that you can always make a step of reduction. Well, why it may happen that it's impossible to make at least one step of reduction? Well, yeah, an example that was written here could help me to answer this question. But as you can see, now it's not here. But let me explain the reason. So if you have just one summand, just this expression, you can reduce it by g, because the leading monomial of this guy is presented in this expression. And the leading monomial of this guy is divisible by the leading monomial of g. So that's why you can at least reduce the leading monomial of this guy by g. By the same argument, if you don't have the first summand, the leading monomial of this guy is the product of the leading monomial of b and the leading monomial of f. So it's divisible by the leading monomial of f, and you can reduce this part of the expression by f. So what can go wrong here? Well, if the leading monomial here and the leading monomial here are the same, and they have the opposite coefficients, like here you have like something like 2 and here -2. And then when you add these two summands together, the leading monomial here and here, they cancel each other, so you no longer have this monomial that you can reduce. So this is the problem that may occur. So let me show you that the leading monomial here and the leading monomial here, they always distinct. So let me show that the leading monomial of AG is never equal to the leading monomial of BF. OK? So indeed, let's assume that it may happen that the leading monomial of AG is the same as the leading monomial of BF. But the leading monomial here is the product of the leading monomials of B and F. And the leading monomial here is the product of the leading monomials of F and G. Now, you see, the right-hand side is divisible by the leading monomial of F. So the left-hand side is also divisible by the leading monomial of F. But the leading monomial of F and the leading monomial of G, they are coprime. So that's why the leading monomial of F must divide the leading monomial of A. So since MF divides this product, and these two leading monomials are coprime, we see that the leading monomial of F divides the leading monomial of A. But all the monomials of A are strictly smaller than the leading monomial of F. So it's impossible. This is a contradiction. So it occurs because of this thing. And why this contradiction happens? Well, because we assume this thing. So our assumption is wrong. So it's impossible to have the leading monomial of the first summand to be the same as the leading monomial of the second summand. But now, if the leading monomials here and here are distinct, at least one of them is higher. Let us assume that the leading monomial of the first summand is larger. So then the leading monomial of the first summand is larger than any monomial here, so it cannot be cancelled. So it's presented here, so that's why you can reduce it by g. If the leading monomial of the second summand is higher, then it cannot be cancelled here because of that statement. So that's why it's present here in the whole summand, so you can reduce the whole summand by f. So in either case, you can reduce this expression by g or f, at least once. Who was able to follow? Are there any questions? OK, now, the second thing that I want to show you, that if you can reduce this expression by g or by f, the resulting expression will be the same expression, well, an expression of the same form. That is to say that these two polynomials satisfy these two properties. So let me show you why. Well, OK, let's assume that the leading monomial of AG is higher than the leading monomial of BF. Let's reduce the leading monomial of AG by G, and let's see what happens. Well, since this is the monomial we're going to reduce, well, it's the product of the leading monomial of A and the leading monomial of G. So how do we make the reduction process? Well, we should subtract G times what? First of all, we should multiply the polynomial G by the leading monomial of A in order to make the leading monomial here the same as here. And then we should multiply this by the corresponding coefficient in order to make the coefficient the same as here. So first of all, we should divide by the coefficient of G, which is C2. And then we should multiply, oh, actually, it doesn't matter. So, and yeah, we don't need to divide by that because G is also here. So we just need to multiply by the leading coefficient of A and subtract this expression because the leading coefficient here is the product of the leading coefficients of A and G. The leading coefficient of G is already here, so we just need to add the leading coefficient of A. So now the leading monomial, so the leading term of this expression is exactly the same as the leading term of this expression. So after subtraction, what will we get? We will get A minus CA MA times G plus BF. And as you can see, we just reduced the leading monomial, so every monomial here is just smaller than the leading monomial from A, and the leading monomial from A was smaller than the leading monomial of F. So these two polynomials, so this is your A prime and this is your B prime, so they also satisfy this property. So that's why you can always reduce this expression, and the result will be the same expression, the expression of the same type. So after finitely many steps, you will get a remainder, which will be an expression of this form. But if this A prime and B prime are not 0, then you can make at least one step of reduction. So this contradicts to the fact that this is a remainder. So in case of remainder, A prime and B prime must be 0. So that's how you can prove this. OK. Yeah. So this is a special case when you can reduce the S polynomial to 0 automatically. Now, let me discuss the reason why we need Gröbner basis. And in order to do this, I want to discuss the ideals in the polynomial ring. So, wrong marker. Ideals in f of x1, xn. first of all, suppose we're given a set of polynomials here. I want to define a set of polynomials generated by G1, Gk. This is the notation, and the definition is H1, G1 plus Hk, Gk, where H1, Hk are arbitrary polynomials here. So this is the definition. So again, we consider all linear combinations of G1, Gk with coefficients being polynomials. Okay? So this is a subset inside the set of all polynomials. Now, what I'm saying that this subset is an ideal. Just in case, who remembers the definition of an ideal? Nice. Who think that I should recall the definition? Okay. I like that you raised your hands 2 times in a row. That's nice. Okay, so what is an ideal? An ideal is a subset of a ring with 2 properties. The property number 1, it must be additive subgroup. So it's a subgroup with respect to addition. So what it means that the 0 polynomial must be here. The set must be closed under addition of polynomials, and the set must be closed under subtraction of polynomials. Well, it's clear that the 0 is here when all h's are 0. Now, if you take 2 expressions of this form and you add them together or subtract one from another one, you will get an expression of the same form, so it's also inside this set. So it's an additive subgroup of this ring. This is the property number 1. The property number 2 says that if you take anything from this subset and you multiply by any polynomial, you will get an element of this subset. But it's clear if you take an expression of this form and you multiply it by f, you will get an expression of the same form. You just change hi by f times hi. That's it. So it's closed under. So the 0 is here. It's closed under addition, subtraction, and multiplication by any polynomial. So this is the definition of an ideal. So it's clear that this is an ideal. OK? Just in case, is there anyone who wasn't able to follow why this is an ideal? OK, good. Now, what is important? Well, in this ring, it happens that every polynomial can be presented, or every ideal can be presented as an ideal generated by G1, Gk. Well, OK, first of all, we will say that this ideal is an ideal the ideal generated by G1, Gk. And what happens is that every ideal can be presented in this form. So there are no other ideals in this ring. So every ideal has this form. OK, so the remark, if I is an ideal here, then I can be presented in this form. So strictly speaking, there exists a finite set of polynomials G1, Gk such that I is equal to the ideal generated by G1, Gk. This is what is called the Hilbert basis theorem. OK, one remark. You can prove this theorem using Gröbner basis. I'm not sure whether I will do this or not, but you can prove this result using the Gröbner basis. Or there is some abstract technique saying that this ring is Noetherian, which basically means what's written here. OK, what should be next? Yeah, now, another thing that I want to say, well, why do we care about the ideals? Well, you see, we actually care about systems of polynomial equations. And it happens that two systems, well, let's say you have, let's say, a remark. Let's say we have one system of polynomial equations and another system of polynomial equations, where f's and g's, they are all here, okay? Then, well, if the ideal generated by these polynomials is equal to the ideal generated by these two polynomials, then these two systems are equivalent. In a sense, they have the same set of solutions. So that, well, actually, it's not true that the opposite, so the claim is not true in the opposite direction, but we know how to reformulate the condition here in order to get the criterion. But for now, it's enough to have this implication. So if we have one ideal, and this ideal is generated by two different sets of polynomials, then these two different sets of polynomials gives you equivalent systems. So that's the first thing why we care about ideals. The second thing, well, we actually can reformulate a lot of problems about the systems of polynomials or other different problems in terms of ideals. So that's why I want to know how to solve effectively some basic tasks about ideals. And one of the simplest possible tasks is the following. You're given an ideal, how to check if a polynomial belongs to the ideal or not. OK, so now, if you want to deal with an ideal effectively, well, OK, let me reformulate it in a different way. So if you have a polynomial ring in one variable, we know the description of all ideals. Every ideal is generated just by one polynomial. Who remembers this? So let me recall. If we have a polynomial ring with one variable, we have a polynomial ring with one variable, and we have an ideal here, then the ideal here is generated just by one polynomial. So it consists of all polynomials divisible by f. Okay? And now, if you want to solve a problem regarding this ideal, it's enough to know how to divide with remainder by f. For example, if you want to check if a polynomial belongs to I, well, it's enough to divide g with a remainder by f, and it belongs to I if and only if r is equal to 0. So the remainder is 0. So this is one of the reasons why you can solve effectively many tasks in case of one variable. This is just an example. Now, if you want to apply the same technique in case of polynomials in several variables, you want to have the notion of remainder to be well defined. So you want to have only one remainder for each polynomial. So this means that if you have an ideal in case of several variables, you know that this ideal is generated by some set G1, Gk. But if you want to deal with this ideal effectively, you want this set to be a Gröbner basis. But if you're given an ideal, it may happen that the initial set of generators that you are given is not a Gröbner basis. So now, an interesting question is the following. You're given an ideal generated by G1 and Gk, and you want to find another set of generators, which is a Gröbner basis. So this is what is called the Buchberger algorithm. So the task. So you have a set of polynomials, f1, fm, here. And we have, let's say, the lexicographical order in lex. Now, you want to find another set G1, Gk, such that, first of all, the ideal generated by F1, Fm is equal to the ideal generated by G1, Gk. And the second one, the set consisting of G1, Gk, is a Gröbner basis. So if you do this, this basically means that now you have a set of generators for your ideal, but this set of generators now a good one. So you can make a reduction in such a way that your remainders are unique. So this is one of the basic tasks. And there is an algorithm that solves this task. And it's called the Buchberger algorithm. So let me explain how it works. So how it works. Now, so we start with the set F1, Fk. Okay? Let's say this is G. The step number one, we produce all the S polynomials for all possible pairs. Just compute all of them. Then we reduce them with respect to G to a remainder. Because we don't know whether it's a Gröbner basis or not. We just know that, well, if it's not a Gröbner basis, then each S polynomial may have many different remainders. So we just find at least one remainder. Just reduce until it's possible. Now, if all the remainders are 0, then the set is a Gröbner basis, just by the Buchberger criterion that was presented at the beginning of the lecture. But if at least one of them is not 0, what we do, we add all the non-zero remainders to the set G. And then we repeat the procedure. So again, so what we do, we have a set of polynomials. We compute all the S polynomials. We reduce all these S polynomials with respect to our set. We get the remainders. We take the non-zero remainders, and we add them to the set. Now we get a larger set. And we proceed in the same way. We take, again, all the S polynomials. We reduce all of the S polynomials with respect to the larger set. Well, we get the non-zero remainders. We add them to the set. And so on, and so on, and so on. So this is how the algorithm works. Now, there are several questions. The question number one. Will the algorithm terminate? Does it terminate? Will it terminate? The second question, does it solve this problem? Okay. Well, the answer to both of these questions is yes. The algorithm terminates, and it solves the problem. Well, for now, I want to skip this problem, why it terminates. Well, the reason why it terminates is based on some auxiliary lemma, which is called Dixon lemma. I will probably prove it during the next lecture. But so there is a reason. It's not very complicated, but like I don't want to be focused on this issue. But let's check why this algorithm solves the problem. Okay. First of all, we need to check that we will not change the ideal when we add the new remainders. Okay. So let's check that if we have G and we added all the non-zero remainders, the ideal generated by G and the ideal generated by this set is the same. Well, first of all, since this set is a subset of this guy, then just by definition, we have disinclusion. Because if we have a larger set of generators, we may have a larger ideal. So this is just by definition. So we need to prove inclusion in the opposite direction. In order to prove the inclusion in the opposite direction, what I'm saying, it is enough to show that each non-zero remainder belongs to the left ideal. Because if every remainder is here, then every remainder can be represented as a linear combination of the elements from G. So every linear combination of the elements from G and the remainders can also be presented as just a linear combination of elements from G. So that's why it is enough to prove this. Who was able to follow this explanation? OK, are there any questions? OK, now, why this is true? Well, first of all, let's see that by definition, the S polynomial of Fi and Fj is here. Because it was a linear combination of Fi and Fj with some monomials and coefficients. So just by definition, it's here. OK? Now, when we make a reduction, what do we do? Just by definition, a reduction is a process where we take our initial polynomial and we subtract some other polynomial, let's say Fk, with some coefficient and some monomial here. So if this guy is a linear combination of elements from G, and we just subtract a linear combination from elements of G, the result is also a linear combination of elements from G. So that's why when we reduce a linear combination from G by an element from G, we will get a linear combination from G. So that's why if this guy was in this ideal, then the result of the elementary reduction is also here. So that's why the result of every reduction is here. So in particular, every remainder is also here. So this thing is proven. Who was able to follow? OK, good. So that's why we see that when we add these things at every step, we will get a larger set of generators, but the ideal is the same. So basically, it means that if you think in terms of systems, so you add some additional equations, they will not shrink the set of solutions. The set of solutions will be the same, but these new polynomials are kind of helpers. Now, what about this condition? Well, if the process terminates, so the reason why it terminates is if all the remainders are 0, then we just terminate the process. But if all the remainders are 0, then by just the Buchberger criterion, the set G is the Gröbner basis. So that's why the condition number 2 is also satisfied, just by Buchberger criterion. So if this algorithm terminates, then it does solve the problem. OK, so this is the algorithm. Now, what should be next? Let me discuss several tasks related to this algorithm. So first of all, as I already mentioned here, the problem is how to check if something is inside of an ideal. It's called the membership problem. So let me explain how to solve the membership problem. So what is the what is the task? We're given the set of polynomials f1, fk. And now we want to check if a polynomial f belongs to the ideal generated by f1, fk. Here is the algorithm how to solve this issue, the algorithm. First of all, we take the set of generators and apply the Buchberger algorithm. And we will get a Gröbner basis generating the same ideal. So now the task becomes this. So the ideal stays the same, but now instead of just a random set of generators, we have a Gröbner basis as a set of generators. Now we should reduce f with respect to the Gröbner basis we obtained, and we'll get a remainder. Then f is in the initial ideal f1, fk, if and only if the remainder is equal to 0. So this is how to solve the membership problem. So in case of the Gröbner basis, this is the criterion. So we can check if something inside an ideal using this reduction algorithm. So it's very similar to this process, and it works if and only if the set of generators is a Gröbner basis. So it's important. So this thing is a Gröbner basis. That's important. That's how to solve the membership problem. Do I want to prove it? Anything here? I believe no. Well, actually, if the remainder is 0, then f definitely belongs to the ideal. I mean, the implication from right to left works even if, even if we apply the reduction process to the initial set of generators. I mean, from the right to left, it's more or less obvious. Who think that it's clear? You see, what does it mean that f can be reduced to 0? By definition, how do we apply reduction? We take the initial polynomial f, and we subtract g1 with some coefficient and monomial. We subtract g2 with some coefficient and monomial. Then probably again g1, then g5, etc. And at the end, we will get 0. So if we move everything to the right-hand side but f, then we can represent f as 0 plus linear combination of g1, gm with some coefficients and monomials. So just by definition, it means that f belongs to the linear, to the ideal generated by g1, gm. So if the remainder is 0, it's clear that f is inside this ideal. Okay? Who was able to follow? Are there any questions, or should I write it explicitly on the whiteboard? Okay. Now, so this is true in general. What do I mean by in general? I didn't use the fact that g1, gm is a Gröbner basis. The reason why we need a Gröbner basis is because we want to prove in the opposite direction. What if it happens that we take a polynomial, its remainder is not 0, while in case g1, gm is not a Gröbner basis, it may happen that the remainder is not 0, but still the polynomial is in the ideal. Just in case, let me demonstrate this effect. I think it's useful to know why you cannot solve this problem without Gröbner basis. So an example, let's take q, x, y, z, and the lexicographical ordering with x, y, z in this order. And we take f to be xy minus 1, g to be yz minus 1, and the ideal is generated by f and g. And let's say h is x minus z. Okay? Now, it's clear that h is not reducible by neither of them, because none of the monomials is divisible by neither of the leading monomials of f and g. So the remainder is x minus z. But if we take fz minus xg, we will get h. So the remainder, so this is the remainder, it's not 0, but h is in the ideal generated by f and g. So if this is not a Gröbner basis, then this claim is not true. So that's why it's important to first to recompute a Gröbner basis in this case, and then when we have a Gröbner basis, we can check this thing using this algorithm. And by the way, this polynomial h is just an S polynomial, the S polynomial of f and g. OK, that was the first problem. The second problem is variable elimination. So let me show you the task. Variable elimination. Probably like that. OK. So what do we have? We have, before going further, I forgot to mention one thing. Here, when we're given a task, we have a set of polynomials, and we ask a question, if f is an element of the ideal. There is no ordering here on the monomial. So this task doesn't depend on the choice of the ordering. So where does the ordering appear? Well, in order to solve this problem, we have to fix some lexicographical ordering. Well, here we fix an ordering. So we can choose any lexicographical ordering we want. Actually, there are many other different orderings that we can use, but, well, we discussed just lexicographical ordering. But when we want to solve this task, we need to fix some ordering. And if you fix a good ordering, then the task may be very easy to compute. And if you choose, like, you should choose wisely. So if your choice wasn't good enough, then the computation could be very difficult. For example, as we discussed, we discussed an example where you choose one ordering, the pair is a Gröbner basis, and it's clear because the leading monomials are coprime, and if you choose a different ordering, then the leading monomials are not coprime, and it's not clear whether it's a Gröbner basis or not. So, so here, this is the place where you can somehow tweak your future. Whether you will suffer or not depends on you and not on the task itself. OK, now the variable elimination. So what do we have? We have n variables. And we want to consider polynomials depending on variables from 1 to k only. So these polynomials, they form a subset here. Now, suppose we have an ideal here. And this ideal is given by a set of polynomials f1, fm. So these polynomials, they depend probably on all the variables. And this is an ideal here. Now, we want to intersect this ideal with this subring. So we want to take this subring and intersect it with the ideal I. So what does it mean? It means that I want to take all the polynomials from this ideal that depend only on the first k variables. So I don't want to consider polynomials depending on variables from k1 to nth variable. OK, now, again, how do we do this? Well, in general, it's unclear because, it may happen that all the polynomials here, they depend on these variables. But you may consider some sophisticated linear combination of these polynomials with some polynomial coefficients such that all these variables will be canceled. So that's why you can produce something non-trivial which depends only on the first k variables. Okay? But it's unclear how to get all these polynomials without these variables. Now, the Gröbner basis to the rescue. What should we do? First, we should fix an adequate ordering. We take the lexicographical ordering, but which order on the variables should we choose? Well, we should take any lexicographical ordering such that xk plus 1, etc., xn are higher than x1, xk. So the ordering between these guys doesn't matter, and the ordering between these guys doesn't matter. But what is important, all the extra variables must be strictly higher than the variables that we want to leave. Okay? Now, any such ordering works. When we fix this ordering, what we do first, we take the set of generators, f1 of m, and we compute, we apply the Buchberger algorithm, and we compute a Gröbner basis. Let's say S, a Gröbner basis. Now, the second stage, when we have this Gröbner basis, we take all the polynomials here from the Gröbner basis such that they depend on x1, xk only. So we take g0 to be all gi's such that gi depends on x1, xk only. Now, the claim is, the answer is the following. The intersection is generated by g0. So this is how to solve this task. So again, you should take the generators of the ideal I. You fix this excluding ordering where the extra variables are strictly higher than the variables we want to leave. Then we find the Gröbner basis for the set of generators. And then when we have this Gröbner basis, we just take all the polynomials here that depends only on x1, xk, and they are the generators of this intersection. Well, actually, we can even say more. The set G0 will be a Gröbner basis for this ideal with respect to the lexicographical ordering corresponding to the ordering of these variables. This is a stronger claim. So this is how to find this intersection. Well, probably it's unclear why do we care about this kind of stuff. Well, first of all, this task has a geometric interpretation. It corresponds to finding what's called, let's say, you have a system of polynomial equations. It forms some subset in n-dimensional space. Then you want to project this subset onto another plane. So this this is more or less, so when you want to find the equation defining the projection, this is the task you want to solve, actually. So you want to define a projection by equations. Another reason why we're interested in this task is because there are different operations on ideals, like you can add ideals together, you can intersect the ideals together, you can multiply the ideals together. And it's really hard to find the generators of the intersection of two ideals. So this task is used when you want to find an intersection of two ideals. So you can reduce the intersection problem to this problem of variable eliminations. OK, I have 5 minutes. What should I do during the 5 minutes? Let me give you one interesting definition. You won't like it, but I hope it will be interesting. Well, in case of one variable, we had this notion of ring of remainders. Now, since we have a notion of a Gröbner basis, we know how to deal with remainders in case of several variables. So can we define a ring of remainders in case of polynomials in several variables? Well, the answer is yes. So the ring of remainders. Now, suppose we have this polynomial ring, and we have an ideal here, which is generated by a set F1, Fn. Now, let's take a lexicographical ordering, and let's find a Gröbner basis generating the same ideal. So we can generate the same ideal by the Gröbner basis G. Now, when we have this Gröbner basis, we can define the set of remainders with respect to G. And I will denote it by this. So this is the set of all polynomials such that G is a remainder with respect to G capital. This is the set of remainders. What does it mean technically? Technically, when G is a remainder if and only if every monomial of G is not divisible by the leading monomial of every polynomial from G capital. So if you cannot reduce G, it means that every monomial here is not divisible by the leading monomials here. So this is the set of remainders. Now, it's clear that this set is closed under addition. So if you take two polynomials from here, let's say f and h, then their sum, f plus h, is also here. It's also a remainder. So it's closed under addition. But it's not necessarily closed under multiplication. But you can define multiplication in the following way. So you just multiply f and h as usual, like polynomials, and then you find a remainder with respect to the Gröbner basis G. So now you just define multiplication like this. So you multiply and then reduce. So this is the same procedure that we had in case of one variable. We just multiply two remainders, and then we should take the remainder of the product, and this is the result. So one can show that the set of remainders here with respect to these two operations is a commutative ring. Now, this is a generalization of this ring of remainders with one variable. Now, there are two remarks. This object depends on two things. It depends, well, on the choice of a Gröbner basis, and it depends on the choice of the lexicographical ordering. Well, one may show that if you have the same ordering, but two different Gröbner bases for the same ordering, then the set of remainders will be exactly the same, and the procedure, well, in this case, the multiplication, will be exactly the same. So if we have fixed lexicographical ordering, but two different Gröbner bases, then the set of remainders with respect to one Gröbner basis will be the same as the set of remainders with respect to the other Gröbner basis. And the multiplication will be the same. So the multiplication here in terms of G1 will be the same as multiplication here in terms of G2. I'm not going to prove this, but I just want you to know that actually this thing doesn't depend on the choice of G. You can take any Gröbner basis in order to deal with this ring. Now, if you change lexicographical ordering to another lexicographical ordering, so you can, if you have lexicographical ordering 1 and lexicographical ordering 2, then the set of remainders will be different. But the resulting rings will be naturally isomorphic. So you will get distinct set of remainders, probably distinct set of remainders. It may happen that you will get the same, but in general, you will get different sets of remainders. But they will be isomorphic. And the isomorphism works as the following. You take a polynomial f here, and you just compute its remainder with respect to the Gröbner basis G2. Let's say f prime. And f must go to f prime. This is how the map in this direction works. And if you want to produce a map in the opposite direction, if you take G from here, you just take its remainder with respect to G1, and G prime, this is where G must go when you want to produce an inverse map. Again, I'm not going to prove this, but this is how this bijection works. One can show that this is indeed a bijection, and this bijection preserves these two operations, so these two rings are the same. So because of these two remarks, well, actually, this procedure doesn't depend on the choice of the ordering and the choice of the Gröbner basis. So it just depends on the choice of the ring and the ideal. And actually, there is an abstract procedure that can produce this ring. And this procedure, well, is called a quotient ring. We didn't discuss this quotient procedure because, well, it's intuitively very hard to understand. And actually, we should start with the quotient groups. So if you have a group and a normal subgroup, you can produce a quotient group. In the same way, if you have a ring and an ideal, you can produce a quotient ring. So there is this more general procedure. If you're interested, then you can learn about this. You can read something. But in general, if you want to deal with them effectively, you need some technique like this. So you need to find something like a Gröbner basis in order to deal with remainders, etc. OK, so this is the final piece of information that I wanted to present today. Thanks for being here. And if there are any questions, please ask. If no, then that's it.